I'm talking about EXAScaler today and where we're going with the future development. And some of these slides I'll go through quickly. We're running a bit late, but everybody knows lots more data, lots of performance coming requirements. And so EXAScaler has been really driving a lot of the storage in the industry for machine learning. And where do we go from here? EXAScaler and Lustre is continuing to be used in the top 8 of the largest computers in the world, 70% of the top 100, and it's continuing to scale. If you can see in the second row here, tens of millions of metadata operations, hundreds of millions of data IOPS, 100 billion files. We basically have no limits to the scalability except for your bank account. We're working with top DOE and international sites to produce systems for the next generation of exascale computing. And really the area that we're working on as well, in addition to performance, that's sort of in the DNA, but also making EXAScaler easier to use, making it out of the box work better for workflows, automated configuration and tuning and things like that. We do have another session. There's a Lustre BOF where we can hear more of the details on some of these new features. This is a slide I like quite a bit. It's showing where did we come from 20 plus years ago and where are we going now. It's nice to see the flash is growing quite quickly on the right side there, the all-flash storage. But we've grown the capacity. It really shows that the architecture of Lustre and EXAScaler is really expandable and flexible to grow into the future. And where are we deploying? This is really the building block for almost all of the new deployments, right? The NV400 is a 2U controller. It's providing a great basis with TLC flash. Right? These are great numbers. If you look at the performance here, this is equivalent to the entire file system of a top 10 computer from 10 years ago. And we're packing what used to be 20 or 30,000 hard drives into a 2U space. That's totally amazing if you see what that is. And coming out this year is, or early next year, is the QLC flash. That's going to really give us a big boost in capacity while maintaining those performance numbers. It's, along with client-side data compression, this is really going to drive the price point down of the capacity storage while giving you, money orders of magnitude improvement in IOPS and storage. And the DNA of EXAScaler and Lustre is, large block I/O. And so we can handle, 64K I/O and without introducing inflation and on the QLC flash. It's really providing the best of breed in terms of utilization of the QLC flash. And how do we bring the price down? Client-side data compression is coming in EXA3, 6.3 I should say. It's parallel data compression on the client side. And so this is utilizing, the multi-core CPUs that are available, doing high compression ratio if you need it, and it doesn't use or minimizes at least the overhead on the server side, so you can really drive the performance without being bottlenecked with the server-side compression implementation. You can have a flexibility to select different types of compression based on files or directories. It can auto-detect, data that's incompressible and not spend your CPU cycles on that. Or if you have, let's say, scratch directories, you don't want to spend CPU cycles on that. You just want to drive it out to disk as quickly as possible. Those are all flexibility areas that we can handle. Random I/O to a single compressed file, that's all possible. So this is an example with a data set that we got from one of the customers of ours in the climate space. And as you can see, we can get very high bandwidth up in the gigabytes a second. This is per core on a client. So we can get nearly a gigabyte a second per CPU core on a client. And so that will actually, if you do, in this case, the LZ4, it's doing almost 2.5 times compression ratio. That saves 2.5 times of capacity, right, on the server side. But it's also potentially improving the bandwidth by 2.5 times. It's improving the network bandwidth by 2.5 times. So you'll actually be able to improve the performance of your system by implementing compression if there's enough clients doing I/O to the file system. And in our testing, we've run over a number of different data corpuses, climate data, scientific data, and realistically, we can get about between 1.5 and 4. Sometimes we hit as high as 6 times compression. Of course, you know, there are some data sets that are already built-in compressed, so you're not going to get anything there. But you know, this is totally transparent to applications and users. They don't have to do anything to enable this. Another area in the machine learning that we're doing is a persistent client cache. It's called hot nodes. And this is allowing applications and compute nodes to persistently store read-only data on the compute side. And so this allows you to have, let's say you have a DGX, it has built-in NVMe storage. You're able to transfer the data, it stores it locally, it's kept consistent with the entire global file system, so you don't have to do things like managing the data. Oh, we updated this data set, is it gonna come out to the compute nodes and be the right version when we're updating? Right, that's all handled transparently, you access it on the first read. If your policy says this is in a directory or a project or a type of file that should be cached on the compute node, it will store it locally, and then we have a policy, either pin it in the compute node for important data sets, or you have a least recently used policy. So this is saving your network and for recent data that's repeatedly used in a training. What you can see here, this is run with our partner NVIDIA, that if without the hot nodes, every time you're doing a training cycle, you're reading data from the network. You're reading the same data over and over and over again. And with hot nodes, in the first phase, you start your computation, it's reading these files, the policy says, this is a data set that we want to cache. And so in parallel with you doing your training, as you're reading these files in, it's also fetching them and storing them into the local cache. And then you can see on the bottom right, the purpley blue bar, there's no network I/O almost on the storage network, and all of the training data comes out of the local cache. And the caveat here is that this is not improving your single job performance really, because the PCI network, you know, to a PCI card going to NVMe is about the same speed as a PCI card going to the storage. We have, you know, 90%, 95% efficiency over the network. But what this is saving you is management. It's saving you the load so that the servers can be doing writes. They can be doing, you know, handling all kinds of different workloads concurrently, and you're not redoing the same thing over and over. Another area that's become much more important in HPC and in machine learning, multi-tenancy, security. You know, we've really improved the environment here, allowing compute nodes to have a subdirectory mount so that they only have an isolated view of a subset of the data system. And in the old days, we were working very hard to, you know, aggregate up enough performance, enough capacity to feed, you know, the beast. And now we're finding that, you know, with the huge GPUs, you need to segment the performance and the capacity into different containers so that, you know, two customers that are running in a cloud space, they're not necessarily able to see their, you know, data. If you have, you know, two car manufacturers, you don't want them to be able to access the same storage, right? And so we have very fine-grained access controls and physical isolation, security, data encryption, persistently and on the network. And we can manage that with QoS to ensure that one client on a compute node is not overwhelming the storage on the other. As well, doing management in this area is improving all the time. We have EMF, which is simplifying the installation, the upgrade, and expansion of the storage. And so in terms of the hardware, like I mentioned, NV400, best of breed performance, 2U, also low power, right? This is very important. Your racks can only feed so much power. You can't afford to put in the GPUs and have storage there without being sure that it's efficient. Expansion, the initial deployment will have 2 of the QLC drawers being able to attach onto each NV400. Going forward, we'll allow up to 4 drawers. These are phenomenal numbers in terms of per rack performance, bandwidth, capacity, utilization. It's very efficient storage. And if you need, the whole spectrum of best price performance, best dollar per capacity, best performance per watt, with EXAScaler and SFA architecture, we can really cover the whole spectrum. And so, this is all available today.